Welcome, dear viewer, to the intricate world of thermodynamics, a realm of science where heat dances with temperature and energy waltzes with work. This branch of physics, as old as the steam engine and as modern as the microchip, whispers the secrets of how our universe operates, from the smallest atom to the largest galaxy. Thermodynamics, a beguiling term derived from the Greek words thermi, meaning heat, and dynamis, meaning power, is indeed the study of heat power. It is the grand stage where heat and temperature pirouette in an eternal ballet with energy and work. It is the silent observer to the cosmic dance of the universe, narrating tales of energy transformations and the ceaseless march of entropy. In this broad theatre of nature, thermodynamics defines a set of macroscopic variables that characterize materials and radiation. Internal energy, the sum total of all the energy contained within a system, is one such vital player. It's the energy that a system possesses by virtue of the positions and interactions of its particles. Then we have entropy, the prima ballerina of thermodynamics. She is the measure of disorder, of randomness, of probability. The universe, it seems, has an inherent tendency towards chaos, and entropy is the mathematical embodiment of this cosmic reality. And let's not forget pressure, the mechanical force exerted by an object's mass and gravity. It's the unseen hand that shapes our world, from the crushing depths of the ocean to the thin, ethereal heights of our atmosphere. Indeed, these variables and more form the foundation upon which thermodynamics is built. They are the threads that weave together the grand tapestry of our universe, a tapestry that is ever-changing, ever-evolving under the watchful eyes of the laws of thermodynamics. Stay with us as we delve into the four laws that govern this fascinating field. A journey awaits, a journey into the very heart of the universe, into the exquisite ballet of thermodynamics. We commence our exploration with the zeroth law of thermodynamics. Now, the zeroth law might sound somewhat peculiar. After all, who starts counting from zero? But in the realm of thermodynamics, it seems we do. This law, named so as an afterthought because of its fundamental nature, lays the groundwork for the rest of thermodynamics. The zeroth law states that if two systems, let's call them System A and System B, are each in thermal equilibrium with a third system, say System C, then System A and System B are in thermal equilibrium with each other. It's a bit like saying if Alice and Bob both have the same temperature as Charlie, then Alice and Bob must have the same temperature as each other. Simple, isn't it? But what does it mean for systems to be in thermal equilibrium? Well, it's a fancy way of saying that there's no net flow of thermal energy between them. If you leave a hot cup of tea and a cold spoon together for a while, the spoon will get warmer and the tea will get cooler until they reach the same temperature. That's them achieving thermal equilibrium. So, the zeroth law is essentially a way of saying that temperature is something we can compare and measure. If System A is in equilibrium with System C and System B is also in equilibrium with System C, then it stands to reason that System A and System B must have the same temperature. They're on an equal footing, thermodynamically speaking. This law is the foundation for the concept of temperature. It allows us to say that one thing is hotter or colder than another, and by how much. It gives us a common language of heat, a way of understanding and describing the thermal world around us. It's the reason why we can use a thermometer to measure temperature, why we can talk about the boiling point of water or the freezing point of ice. It's the reason why we can say with confidence that today is a hot day or a cold day. The zeroth law, then, establishes a fundamental concept: temperature. Next, we venture into the realm of the first law of thermodynamics. In this realm, we find a law that is as unyielding as it is profound. This law, friends, asserts an immutable truth about our universe. Energy cannot be created, nor can it be destroyed. It is a law of nature that stands unwavering, unyielding and unassailable, a law that rules supreme in the cosmos. Let's delve a bit deeper. Imagine, if you will, a stage. On this stage, energy performs an intricate dance, shifting and transforming, but never disappearing. It may change its costume, from kinetic to potential, from thermal to chemical, but it is always there, part of the grand performance of existence. Our journey continues with the second law of thermodynamics. As we delve deeper into the realm of thermodynamics, we encounter a law that is as unyielding as it is profound. The second law of thermodynamics, a cornerstone in our understanding of the universe, states that the total entropy or disorder of an isolated system can never decrease over time. Imagine a cup of hot tea in a cold room. Left to its own devices, the tea cools down, transferring its heat to the surrounding air until an equilibrium is reached. This is entropy in action, an ever-increasing state of disorder. The heat doesn't flow back from the room to the tea, making the process irreversible. The second law of thermodynamics also gives us the concept of irreversibility. It's like a cosmic arrow pointing in the direction of time's march. Energy flows from a hotter body to a cooler one, not the other way around. It's why the sun's heat radiates outwards into the cold void of space, or why ice in a glass of lukewarm water will melt, not freeze. This law paints a picture of a universe that is gradually running down, like an unwound clock, its energy dispersing into a higher state of entropy. It may seem a little bleak, but it's also quite liberating. It tells us that we're part of a universe in constant motion, forever changing, forever evolving. Yet the second law isn't just about the flow of energy or the increase of disorder. It's also about information. It's woven into the fabric of our understanding of black holes, of quantum mechanics, and even of life itself. It underpins the process of natural selection, the evolution of complex organisms from simpler ones. All these processes increase entropy, creating a universe that is complex and wonderfully disordered. So the next time you're sipping a hot cup of tea, remember the second law of thermodynamics. It's not just about heat and cold. It's about the very essence of life, the universe, and everything in between. The second law hence provides a key principle: entropy increase. We conclude our exploration with the third law of thermodynamics. This law is a rather interesting one, and perhaps the most intriguing of them all. It postulates that the entropy of a system approaches a constant value as the temperature approaches absolute zero. Now that's a mouthful, isn't it? So let's break it down. Entropy, in its simplest terms, is a measure of disorder within a system. It's a bit like the mess in your room. The more disordered it is, the higher the entropy. Now imagine if you could cool your room down to absolute zero, which is the lowest temperature possible, around minus 273.15 degrees Celsius. According to the third law of thermodynamics, the entropy or the disorder would reach a constant value. But what does this mean, practically speaking? Well, it means that at absolute zero, substances tend to order themselves into the most compact and orderly state possible. They become perfectly ordered, with no room for chaos or disorder. It's as if your room not only tidies itself up, but also arranges everything in the most efficient way possible. However, reaching absolute zero is not physically possible. You see, to reach this temperature, you would need to extract all the heat energy from a substance. And that's just not possible with the technology we have today. Even in the vast coldness of space, the temperature hovers just above absolute zero. This law, therefore, reveals something fascinating about the nature of our universe. It tells us that there is a fundamental limit to how cold things can get and how ordered they can become. It tells us that there's a limit to the calm, a limit to the stillness. So you see, the third law of thermodynamics is not just about temperature and entropy. It's about the fundamental limits of our universe, about the boundaries that nature has set for us. The third law, thus, reveals a fundamental limit: absolute zero.